From this video, we'll start discussing the second-order ODEs. Just to quickly recap, for first-order ODEs, it has the general form of y prime plus pxy equals to rx. Naturally, if you extend the concept for second-order ODEs, it will have the general form y double prime plus pxy prime plus qxy equals to rx. If Rx is equal to 0, we call it is homogeneous. If Rx is not equal to 0, we call this is non-homogeneous. This is exactly the same as what we have learned back in the first-order ODEs. Let's look at a special example of the second-order ODE in a very simple format. Y double prime plus y equals to 0. If we compare this format to the general form of second-order ODE, px is equal to 0. Sorry, I made a mistake in my written note. Then qx is equal to 1 and rx is equal to 0. You need to show that y equals to cos x and y equals to sin x. These are the solutions for this second-order ODE. The process is very straightforward. When y is equal to cos x, y prime is equal to minus sin x. Y double prime is equal to minus cos x. If you do substitution, you will get 0. Similarly, if y is equal to sin x, y prime is equal to cos x, y double prime is equal to minus sin x. Again, if you do substitution, the sum will be equal to 0. So far, everything seems to be very straightforward, and this will lead to a very important theorem. If y1 and y2 are two solutions of one second-order ODE, then any linear combinations of y1 and y2 are also solutions for this second-order ODE. To write that down mathematically, y equals to c1y1 plus c2y2 is the general form of solution. Now, let's take a step forward and set the boundary condition. Let's write down this equation again. Y double prime plus y is equal to 0. If you know y naught is equal to 3, y prime 0 is equal to minus 0.5. Do some simple calculation. You can unambiguously calculate the y value. Y is equal to 3 cos x minus 0.5 sin x. Let's do a very small change to the previous equation. By changing the plus into minus, now we have y double prime minus y equals to 0. The solutions can be y1 equals to exponential x and y2 is the exponential of minus x. From the quote-unquote important theorem, you know the general solution will be y equals to c1 e to the power of x plus c2 e to the power of minus x. This video is very easy, but the takeaway message is very important. In the form of y double prime plus or minus y equals to 0, you know that the solutions are either in sine and cosines or in the exponential form. You will see their applications to solve physics problems in the next video.